In this video, we're going to introduce the temporary notion of solvable by Ruffini radicals. This is there will be a definition that really just only exists for this this chapter. But what we saw was that if we looked at rational functions in T1 through Tn, where we're imagining that T1 through Tn are roots, although they don't need to necessarily be roots, that we have these expressions in T1 through Tn, namely S1 to Sn, S1 being the sum of all the T's, S2 being all the pairwise products, and so on, are elements there. So these are polynomials in the T's. And so we can look at the field, the subfield generated by C adjoin S1 through Sn sitting inside of T1 through Tn. Right? Every element on every one of the S's is on the right. So we can look at the field generated by it. And these are not equal to each other. That's a fact. It turns out that all polynomials, this is called the fundamental theorem of symmetric polynomials, any symmetric polynomial, which is just a polynomial that is left unchanged when you permute the T's, is an expression in the S's. And so these S's that we saw before, these have a name. These are called the elementary symmetric polynomials. They're elementary in the sense that they are the building blocks for all symmetric polynomials. So any symmetric polynomial is an expression in these. Okay, that is said differently, if sigma is any permutation, so equivalently, if sigma is in Sn is any permutation, and P of T is in C adjoin T1 through Tn, is P of, I'll put T underlined to indicate it's a vector, is such that when I apply sigma to the indices of the T's, we get P of T back. Then actually P of T 1 through Tn, you can write it in terms of a product of the S's. Okay, so just do a quick example of that. So T1 squared plus T2 squared is a symmetric polynomial because it's invariant under swapping 1 and 2. And S1 was T1 plus T2, right? And S2 was T1 times T2. S1 squared is T1 squared plus 2T1 T2 plus T2 squared. So S1 squared minus 2T1 T2 is the thing we want, T1 squared plus T2 squared. And T1 T2 is S2. So we were able to express T1 squared plus T2 squared in terms of the two symmetric polynomials. All right, so what we have here then is we have an extension. We have an extension where the symmetric polynomials in the T's are sitting inside of, let me write it in our normal notation, sitting inside of the just rational functions in T. And so we have a definition. We say that the polynomial equation f of t is 0 is soluble. I think I wrote solvable in the beginning, but I meant soluble by Ruffini radicals if there exists a finite tower of subfields or intermediate fields where you start with the symmetric ones. This is where f makes sense, right? Because the coefficients of f are symmetric polynomials in the roots. So f is defined here. I mean, f is defined everywhere because it's over C, but this is sort of like if I were to put a q here, this is the smallest guy where f makes sense if f was over q. Or you know what I mean. So this is the start of the extension, and then we have a finite extension, so it stops at some point, and at the stopping point we've gone to all polynomials in T, such that we could do a lot. There's a lot of ways in which we could build an extension, but there's a condition such that for j equals 1 to r, kj is kj minus 1 alpha alpha, this makes sense. Yeah, alpha j. And alpha j to the nj is in kj minus 1 for some power. All right, what in the world is this saying? This is saying that we build a tower of extensions by adding in roots. What this is saying is alpha j is an njth root of an element of kj. So the alphas that we're adding are just roots. So we go from one to the next by just adding in roots. A root is a radical. Okay? So that's what we're saying here.